Section: Introduction. In this section, we discuss what we mean by 3D-aware visual representations. When we look at a scene, we can understand its 3D structure even though we only see a 2D projection. Research in psychology suggests that our perception includes surface properties like depth and orientation. Studies on mental imagery indicate that our internal representations of objects show their 3D shape and follow 3D rules. Based on this research, we believe that 3D-aware representations include basic 3D properties like distances and orientations of surfaces. These representations should remain consistent across different views of the same object or scene, as they come from the same underlying 3D geometry. Visual representations in computer vision have varied in how well they show the 3D shapes of objects. Early representations explicitly depicted 3D geometry, while recent approaches focus on dense feature grids or sets of tokens. However, it's unclear what these learned representations encode or how 3D-aware they are. Common interpretability methods like GradCam show which parts of the image influenced a specific decision, not what information the network represented. To evaluate the 3D awareness of visual models, we propose testing them on two abilities: single-view 3D and multi-view consistency. Drawing inspiration from human perception studies, we assess how well models encode basic 3D properties and how consistent they are in a 3D context. For a single image, a 3D-aware model should accurately show the visible surface and include features like depth and surface orientation. When given multiple images of the same object or scene, a 3D-aware representation should capture the relationships between the images and provide accurate correspondence. While these capabilities don't cover everything, they address two key aspects of 3D understanding and relate to common computer vision problems like estimating depth, surface normals, and correspondence. Section Summary. In this section, we delve into the concept of 3D-aware visual representations, which aim to capture the fundamental 3D properties of surfaces like distances and orientations. We explore how visual foundation models, despite being trained on 2D data, can implicitly represent depth and surface normals in images of scenes and faces. By evaluating these models on single-view surface reconstruction and multi-view consistency tasks, we aim to understand how well they encode 3D geometry and establish accurate correspondence across different views of objects or scenes. Section: Experimental Setup. In this section, we aim to assess the 3D understanding of visual backbone models through our experiments. Our focus is on vision transformers that serve as general backbones for various tasks and have been trained with different supervision methods. We consider tasks like classification, language supervision, self-supervision, text-conditioned image generation, depth estimation, and class-agnostic segmentation. These models show promising generalization capabilities across different domains. To ensure a fair comparison, we use publicly available checkpoints with similar architectures and training scales. To evaluate the models, we avoid fine-tuning, which may bias the results, and instead use trainable probes and zero-shot inference methods. This approach allows us to assess the model's pre-trained representations without altering their weights or capacity significantly. For single-image surface reconstruction, we analyze how well the models capture the visible surface in images by performing depth estimation and surface normal estimation tasks. Depth estimation involves predicting the depth of each pixel, while surface normal estimation predicts the surface orientation at each pixel. We use dense probes inspired by the DPT decoder for this evaluation, deviating from the common linear probing approach. Our probes are trained for 10 epochs using the Atom W optimizer with a learning rate scheduler. We find that longer training does not significantly improve performance due to the probe's limited capacity. Section Summary. In this section, we aim to evaluate the 3D awareness of visual foundation models by analyzing their ability to represent the visible surface and consistency across views. We focus on vision transformers trained with various supervisory signals like classification, language supervision, self-supervision, depth estimation, and class-agnostic segmentation, using dense multiscale probes for depth and surface normal estimation tasks. Our approach involves training the probes for 10 epochs with the Atom W optimizer and a linear warm and cosine decay learning rate scheduler to assess the model's 3D representation capabilities without altering their weights or capacity. Section: Datasets. In this section, we assess the performance of various models on scenes and objects using different datasets. We use the NYUV2 dataset to evaluate scene-level performance and the Navi dataset for object-level performance. Both datasets provide aligned depth maps. We also generate surface normal annotations for the Navi dataset. Our evaluation focuses on qualitative results and performance trends. We analyze whether models can effectively represent depth and surface normals. We find that some models perform well in encoding depth and surface normals, while others struggle. The performance of models is strongly correlated across different tasks, indicating that they are learning to represent surface information without task-specific supervision. Discriminative self-supervised models perform best across tasks and domains. We also evaluate the model's ability to maintain consistency in representing visible surfaces across multiple views using correspondence estimation. We find that while models can estimate accurate correspondence for small viewpoint changes, their performance deteriorates for larger viewpoint changes. Current models are not consistently 3D aware despite encoding surface properties. Semantic correspondence, which matches similar semantic parts across different instances of the same class, may capture both 3D structure and semantics, but it is susceptible to semantic biases in the data. Section Summary. In this section, we evaluate the performance of models on scenes and objects using datasets like NYUV2 for scene-level assessment and Navi for object-level evaluation, both providing aligned depth maps. We find that models vary in their ability to represent depth and surface normals, with some achieving high accuracy while others struggle, highlighting the importance of diverse benchmarking tasks. Additionally, we explore the consistency of representations across multiple views for 3D understanding, observing that while models can estimate accurate correspondence for small viewpoint changes, their performance deteriorates for larger changes, indicating that current models are not yet fully 3D consistent despite encoding surface properties. Section: Analysis. In this section, we explore how different tasks are correlated in visual models. We investigate if a model's ability to represent depth also makes it useful for correspondence tasks. To answer this, we analyze the correlations between the model's performance across various tasks. We focus on understanding how training objectives relate to 3D awareness. While we discuss specific models in our analysis, we actually evaluated a larger set of model variations and calculated performance correlations across tasks for the entire set. You can find the complete results in the appendices. We calculate the correlations between all task pairs using the Pearson correlation coefficient. For tasks like single view 3D, we look at recall for depth and surface normal estimation on objects and scenes, as well as correspondence estimation. We also examine performance based on viewpoint variation for tasks like Navi and ScanNet. Additionally, we analyze the overall performance for semantic correspondence estimation. We observe strong correlations, coefficients above 0.82, among all single-view tasks. However, the correlations across multi-view tasks are weaker, as indicated in the correlation matrix. Surprisingly, semantic correspondence performance shows stronger correlations with single-view tasks than with multi-view tasks, even though the evaluation procedures are similar. This reinforces our argument that semantic correspondence may not be a reliable measure of 3D consistency. Our work is connected to previous studies on understanding the representations learned by vision models for 3D tasks. We build on efforts to assess the semantic and localization capabilities of visual backbones, extending them to 3D awareness. While some research has focused on generative models' ability to capture single-image geometry, we concentrate on dense probing tasks and multi-view consistency to avoid biases from semantic priors that can affect 3D understanding. We also investigate how large-scale models can be used for tasks like correspondence and pose estimation, as well as fine-tuning for depth estimation. Our analysis differs from these approaches as we aim to comprehend 3D awareness in models trained without 3D supervision. In summary, our study delves into the 3D awareness of visual models, examining how well their representations capture the 3D aspects of scenes and objects. We believe that 3D awareness involves representations that encode visible surface geometry and remain consistent across different views. By evaluating frozen model features using trainable probes and zero-shot inference methods, we find that most visual foundation models encode depth and surface orientation accurately, except for vision language models. While models perform well in estimating semantic correspondence and correspondence within similar viewpoints, they struggle with large viewpoint changes, indicating a lack of multi-view consistency. This suggests that models may be learning view-specific rather than 3D consistent representations. Our findings may spark further interest in understanding how visual models perceive 3D space, with the hope that future research can provide more insights into their learning processes.